Hello class, and welcome to week 7. Very often, tasks that need to be resolved are attached with hard constraints. Thus, in order for a task to be solved, we need to discover what limitations it's giving us. James Phelan, who is actually a famous Russian professor and translator, wrote a poem about this very thing that applies perfectly to the study of artificial intelligence. He wrote, "Every task involves constraint. Solve the thing without complaint. There are magic links and chains forged to loose our rigid brains. Structures, strictures, though they bind, strangely liberate the mind." From his elegant poem, we can see that humans, in order to resolve the tasks, need to use their minds to discover the constraints that govern the task first. In previous lectures, we try to reason in terms of states. However, very often it is better to describe states in terms of features, and then reason in terms of features as well. Example, with planning and scheduling. While planning and scheduling, the agent must assign a time for each action that must be carried out. In such a situation, we will have two types of constraints: constraints on when actions can be carried out, and constraints specifying that the actions must actually achieve a goal. For example, if your to-do list says to pick up your daughter at soccer at 4:30 p.m., and then you need to pick up your son at baseball at 5:30 p.m., you have constraints on when you can do those things. And you also have constraints that you actually have to pick up your kids. You can't just leave them at the fields. So in this week, we will learn how to generate assignments that can satisfy a set of constraints like that. Here are some simple examples of constraint satisfaction problems. The first one is a cryptography problem. Consider the letters in the words study, AI, every day. If we were to replace each letter with a different number so that the sum of all the numbers equaled, say, 103, we would have to figure out which distinct digits we could put in to substitute for those letters so that the resulting sum correctly equals 103. With a map, we are given a map, or a planar graph, and we're told to color it using 3 different colors, green, red, and blue, so that no two neighboring countries have the same color. Or an n-queen problem. Let's pretend that we're playing chess, and so the local condition or constraint is that no two queens may attack each other, and that no two queens are on the same row, column, or diagonal. So how would you arrange your chessboard so that those two constraints are satisfied? By analyzing all 3 problems, we can see clearly that all of them are instances of the same pattern. From the previous examples, we could see that the constraint satisfaction problems have a set of common characteristics. We can use those characteristics to identify a problem in a constraint satisfaction problem and also look for a solution. Such characteristics are a set of variables, such as x1, x2, all the way to x infinity. And for each variable, xi, a domain di with the possible values for that variable, and a set of constraints or relations that are assumed to hold between the values of the variables. The constraint satisfaction problem is to find, for each I from 1 to n, a value in di or for xi so that all constraints are satisfied. Usually we represent constraint satisfaction problems as undirected graphs. In such graphs, nodes are the variables and the edges are the binary constraints. To resolve a constraint satisfaction problem, we use 3 solution methods. First, generate and test. Second, backtracking. And third, consistency driven. First, with the generate and test method, we generate all variable possible assignments, and then we test, does each variable satisfy each constraint? We implement such problems by using nested loops, where in the inner loop we test each constraint. Since for each variable we create a loop, this method is usually pretty slow. With the backtracking method, we try to first order the variable in such a way so that it will be with those more highly constrained or with smaller ranges. Next, we assign values to variables, and we check constraint satisfaction at the earliest possible time. However, if the constraints involving the currently bound variables are satisfied, we will extend the assignment. Consistency-based algorithms use information from the constraints to reduce the search space as early in the search as it is possible. Consistency-driven algorithm is a constraint satisfaction problem is I consistent if for any choice of domains dj1, dj2, all the way to dji, and for any choice of values in the first I-1 domains, there is a value in dji, such as the I tuple consisting of all of these values will not violate any constraint, i.e., it is consistent. When a constraint satisfaction problem is I consistent, for I equal to 1, we say that the problem is node consistent. And when I is 2, we say the graph is arc consistent. For more information, visit your online textbook, Artificial Intelligence, The Foundations of Computational Agents, Chapter 4. Remember that the link is available in this presentation as well as in the reading section of Week 7. And please also look at any other resources in your week before completing your discussions or assignments.